So we've seen previously that historically, when people wanted to design an encryption scheme, they could do it quite easily by writing down something like a substitution cipher. The specification and description was compact and the scheme was easy to implement. But it wasn't terribly secure. And we saw the movement to greater security together with increased practicality has meant a kind of Lego-like approach where we are going to be building high-level primitives using atomic primitives as starting points. It's no longer going to be possible to write down a practical, secure scheme very simply. We will have to rely on knowledge of these building blocks and code for them and so forth. And so our journey into understanding this will start from these building blocks, and one of the most important building blocks is a block cipher. So we'll talk a bit about block ciphers. It'll be largely a historical, empirical kind of study, just to see how people are designing these objects. They're quite intriguing. A lot of the design is art, and it's not always clear why something is the way it is, other than people who understand these things intuitively very well have come to the feeling that that's the right way to do things. But they're very surprising and interesting little objects. But we'll start with some notation and background. You've probably seen this joke a few times, and it's just to explain that we'll also be working mostly in binary. So in binary, recall that 0, 1 to the n is the set of all n-bit strings, and 0, 1 star is the set of all strings of finite length. So it's an infinite set, but everything in it is a string of finite length. The empty string is denoted epsilon. When you put bars around an object, it returns a variety of different things depending on the type of the object. If it's a set, bars around it denotes its size. That's it if it's a finite set. So for example, the set of 2-bit strings has size 4. If you have a string and you put bars around it, you get back its length. For example, the string 0100 has 4 characters or symbols and is length 4. When m is an integer, z sub m is the set of integers between 0 and m minus 1. Intuitively, all remainders that you can get on dividing things by m. And a common operation is picking something at random from a finite set S. So x with an arrow and a dollar sign means that we choose x from the set S such that the probability that x equals any particular element of that set is 1 over the size of the set. So every element in the set is equally likely. One step up from strings as functions. A function is a map that takes certain inputs to certain outputs, and it's important in studying functions that we pay attention to and be clear about the domains and ranges. This means the sets from which the inputs are taken and the sets in which the outputs lie. So if x1 through xn are sets and y is another set, then if we write f colon x1 cross xn to y, we mean that the function f takes inputs x1 through xn, where each of them belongs to the corresponding set. So n inputs and 1 output y, which belongs in the set uppercase y. So n is the number of inputs, or also arguments, and the cross product of those x sets is the domain and y is the range. As an example, the function f from z2 cross z3 into z3 defined as follows. It takes 2 inputs, since there's 2 sets there. It adds them and returns the result mod 3. So n equals 2, the domain is z2 cross z3, range is z3. We're interested for cryptography in a particular class of functions which are permutations. very roughly because permutations allow unique decryption. Here we are considering a function of one argument. It takes input from a set X and returns outputs in a set Y. Now, of such functions, we want to distinguish some and call them permutations. And what allows F to be a permutation is the following properties. First, the domain and range are the same set. So the sets X and Y are the same. And second, there is a unique way to go backwards. So there is a function F inverse going from Y into X. And the property it has is that if you take any point X in the starting space, you apply F to that. So you get a point in the ending space Y. Now you apply this F inverse function, it'll uniquely recover X for you. And a result of this, or an equivalent way of saying it, is that the function F must be one-to-one and onto, or in more mathematical language, injective and surjective. For every point in the range, there is one and exactly one input such that F applied to that input gives you this output. You're not allowed to have two inputs mapping to the same output, nor are you allowed to have zero inputs mapping to any particular output. Now, this definition is purely mathematical. It doesn't say anything about how hard the inverse is to compute or find. That's going to be a different question. Here's an example of functions mapping 2-bit strings to 2-bit strings. So the domain and range sets are both 0, 1 to the 2. We display them via a table. So we show all possible inputs, which are all possible 2-bit strings. And for each, we show an output, f of x. So if you look at these, we show two possible functions. You might notice that the first one is a permutation and the second isn't. Why is that? In the first case, we see that you can go backwards uniquely because for every point here, there's only one x that could yield it. In particular, these 4 points are all different from each other, and every 2-bit string appears here. So every 2-bit string appears once and exactly once here, and that allows us to go backwards. This is not a permutation because the string 1, 1 appears twice. So if you were needing to invert 1, 1, you wouldn't know what to do because both this input and this input could be possible inverses, and so no inverse is uniquely defined. If it's a permutation, we can write an inverse, and it simply reads this table backwards. So it would say 0, 0 maps to 1, 0, 0, 1 maps to 0, 0, 1, 0 maps to 1, 1, and 1, 1 maps to 0, 1. Now, cryptographers don't want to look at just a single permutation. They want the ability to associate permutations with keys. And that means there's actually going to be a set of these permutations, and different keys will allow you to grab different ones of them. So formally, this is captured as a family of functions, or function family, which formally is itself just a function. It's a 2-input function, which means that its domain is the cross product of 2 sets. The range is a single set. We'll call the first set keys because its elements play the role of keys, and we'll refer to the second set as the input space. So we have then a set of keys, the key space, this set D, the input space, and we'll refer to this range R as the output space or range. Now, often in our examples, these sets will be sets of strings of fixed lengths. For example, keys will often be the set of strings of some length k, in which case this k is the key length. And if this is the set of all strings of some length L, that becomes the input length. Correspondingly, if the range is a set of all strings of some length big L, then big L becomes the output length. Often what we're interested in is what happens when we fix a particular key. When we do that, we obtain a function from D into R. We denote that function by f sub k. How is that function defined? Well, on an input x, it just runs the two-input function on k and x. But it itself takes only one input. The key k is fixed as far as this function is concerned. A lot of our interest will be in the properties of this function. Okay, so here's an example. So if we define f as shown here, the space of keys is this, z2. Remember, that means just the integers 0 and 1. The space of inputs is this, which is the integers 0, 1, and 2. Space of outputs is also 0, 1, 2. And the formula we've used is that you multiply the key and the input, which are both integers, to get an integer result and take the result mod 3. So what about this style of functions? If we fix the particular key 1, why can we fix that key? Because it belongs to this space. It's a possible key. Then the function you obtain maps this set into this set and is obtained by taking this formula and setting k equal 1. So 1 times x is x. So the function is just x mod 3. Finally, or perhaps surprisingly quickly, we can come to an object of cryptographic interest for us here, which is the main concern, which is a block cipher. So here we start from a family of functions. Some families of functions are called block ciphers, and we're going to say what allows us to do that. Being any family of functions, it has a space of keys, a space of inputs, and a space of outputs. To be a block cipher, it will additionally be the case that the input and output spaces are the same. They're the same set. The second condition refers to those individual functions. Recall that if I take a particular key from this set and fix it, I get a function from D into R, which is now from D into D since R is the same as D. I can ask whether that function is a permutation. Is it the case that this function is one-to-one and onto and has a unique inverse? If that is true, for every choice of the key, then I declare E here to be a block cipher. So what does this mean? It means that there is for this E sub k a function ek inverse. It also maps D to D going this way, and it has the property you expect from a permutation, which is that if you apply the first function to some x, get a result, and then apply the inverse function, you just get your input back. You can uniquely recover the input from the output. But remember, this has to be true for every key. For every key, there is such an inverse function. If it exists, we will let E inverse, written like this, denote the family of functions. So now it takes two inputs to one output, that whose individual functions are these inverses. So this family of functions on input k and y returns this function applied to y. And we call that the inverse block cipher. And one thing you can check is that it itself is a block cipher, meaning it meets this definition. The inverse of this is, of course, just E itself. Now, again, in this description, we don't talk about any computability properties, but in practice, we want these block ciphers to have compact descriptions. We want them to be easy to implement in software and hardware and things like that. And those we'll see in specific examples. And recall that usually the set of keys is a set of strings of some length k, which is the key length, and often also the set of inputs and hence also outputs is the set of strings of some other length. And here we call that the block length, and that's kind of where the name block cipher comes from. So we can represent block ciphers in many ways. We might write code, we might write formulas, but one thing which represents any block cipher is a table. How would we do that? For example, if we have here a block cipher taking 2-bit keys and 2-bit inputs to 2-bit outputs, then we can create a table where the columns are labeled by possible inputs, the rows by possible keys. And in every row, we write the function determined by the key indexing that row. So this says E of 0, 0 is 1, 1, E of 0, 0 and 0, 1 is 0, 0, and so forth. So you read the table in the natural way. And each row corresponds to one of these E sub k functions. How do we check that it's a block cipher? We notice that in every row, we have a permutation because the points in every row are exactly all 2-bit strings, each 2-bit string appearing exactly once. No 2-bit string is omitted, no 2-bit string appears twice. And those properties tell us it's uniquely reversible. If you know what row you're in, you can go back from outputs to inputs. That is embodied in here. This represents the inverse cipher. Here again, now these are the possible outputs, and these are again the possible keys. So how do we get this? Well, when the key is 0, 0, what is the inverse of the point 0, 0? Well, we see here that 0, 0 arises from 0, 1. So we put 0, 1 here. 1, 1 arises from input 0, 0. So we put 0, 0 here. And so on. So try another example. If the key is 1, 0, then input 0, 0 maps to 1, 0, and that should mean that output 1, 0 should map to input 0, 0. Sometimes it's confusing to consider that properties, or it maybe helps avoid confusion, to think about things that block ciphers don't guarantee. So here in this table, notice that this row of E and the corresponding row of E inverse are the same. So you see the same entries here and here. What does that mean? It means that the function induced by key 0, 1 is the same as the inverse function induced by key 0, 1. That is not a requirement for a block cipher, it's just a coincidence. It happens to be true in this case. Rows have no repeated entries. That's a requirement. Why is that? Because that's what guarantees the permutation property for any given key. It will be true both for the cipher and for its inverse. While rows are not allowed to have repeated entries, nobody said that columns are not. So look at this column, and you see one entry actually appearing 3 times. That's not a problem. That doesn't contradict the permutation property because that's on a per key basis. It's also the case that here, 2 rows of the block cipher are the same. It says that there are 2 keys which induce exactly the same functions. That's okay. That's not a property that block ciphers are either required to have or required not to have. You may or may not have it. Another way of specifying block ciphers is in code. So we might write a simple formula. For example, here, setting the key length and input length to the same, we have a block cipher with k-bit keys and l-bit inputs and l-bit outputs, which on input k and x just returns k XOR x. You can see analytically that it has an inverse, and the inverse also has a formula, and the formula is actually the same. You just add k to y. You can check analytically that this inverse works because if you evaluate ek inverse on the result of ek on x and you plug in the formulas, well, the first one is k plus x and the second one adds k again, and so the two k's cancel out and you get bad x as you want. The inverse block cipher is simply defined as the two-argument function, which returns this. The difference between that and this is the number of arguments. So understanding the structure of block cipher is just a question of understanding mathematical language, and it's good to get used to that so you can use this language effectively. And a small test question might be that suppose E is a block cipher from a certain set of keys and an input space to the same space. Is it a permutation? And you can think about the answer to that, and the suggestion is to take it slow, as this book indicates. What that means is don't try to answer this straight away by blurting it out. Instead, understand that both a block cipher and a permutation are well-defined mathematical objects. To answer the question, you need to go back, look at the definitions, and then use that to draw a conclusion. So after having looked at the definitions and pattern matched them, you might see that the answer, depending on how you think about it, is either no or that it doesn't make sense. Why is that? Well, for example, because block ciphers have two inputs and permutations just have one. That's enough to rule out there being the same thing. Nonetheless, people often mistakenly refer to block ciphers as permutations, but they aren't. What's a permutation is each individual function induced by each individual key in a block cipher. So here's a little exercise to figure out whether something is a block cipher or not. Suppose I give you back the example we had earlier, function from Z2 cross Z3. So the key space is Z2, input and output spaces are Z3, and you have a formula defining what it does. Is it a block cipher? Why or why not? Again, don't try to jump to a conclusion, but go back to the definition and check it out. What does the definition say? The first thing it asks you to check is the input and output spaces must be the same. Are they? Yes, they're both Z3. So that's a check mark. If that failed, you would already know it's not a block cipher. But there's more. Is it the case that for every possible key in Z2, the induced function is a permutation? That requires us to check what happens on all keys, two different keys. So we can go through that check. And what we notice is right away for the first key, it fails. Why is that? Suppose the key is 0, then we have, what is f0 of 1? It's 0 times 1, which is 0. What is f0 of 2? 0 times 2, which is 0. Both mod 3, but the mod 3 wouldn't make any difference here. These being the same means f0 isn't a permutation. A permutation is not allowed to have collisions. Now, that was just one key. We could fix the other key, f1, and ask whether f1 is a permutation. It turns out the answer is yes. f1 of 1 is 1 times 1 mod 3, which is 1. f1 of 2 is 1 times 2 mod 3 is 2. f1 of 3, f1 of 0 is 0. f1 of 1 is 1. f1 of 2 is 2. f1 is the identity function. So it is a permutation. What does that tell us about f itself being a block cipher? It's not. Why not? Because the requirement is it has to be that for every possible choice of key, a permutation is induced. If there's a single choice for which it's not induced, then f is not a block cipher, and that's what happened here. Okay, so that was just about a little structure and language, but it occurs everywhere, so we need to keep that in mind. Now we're going to start thinking about security a bit more. If we think about block ciphers just mathematically, as we've seen so far, they will either have or not have useful cryptographic properties depending on how they're designed, and we want to distinguish ones that have some good properties. To do that, we need to think just a little bit about how they're used. This will not be very precise, nor will it capture everything we're interested in, but we need a little bit of intuition as to what we're seeking. So suppose we want to use a block cipher for encryption. The way we'd do that is we'd start out by picking a random key from the key space of the block cipher. We imagine here that the block cipher itself is public, so everybody knows the description of the algorithm. It's usually a piece of code or a somewhat lengthy formula, and everyone can evaluate that if they have the inputs on which to do so. So this key is randomly chosen and is provided to the sender and receiver, here called SNR, but not given to the adversary. Again, how this happens is considered magic, but let's assume that somehow the sender and receiver are in possession of this key, and they want to use it to encrypt data. The data they can encrypt are simply L-bit strings, points in the input space of the block cipher. And so the sender, when she wants to encrypt as message XI, will apply the block cipher with the fixed chosen key that she shares with the receiver to that input to get an output and transmit the output. This is done for many inputs, so the receiver gets a string of outputs of the block cipher. Now we see why the block cipher property is important. Since E sub k is a permutation, the receiver can decrypt by using the inverse function associated to k. Since the receiver knows k, it can evaluate that inverse function. It has both inputs, the key and the output y sub I, and it will recover x sub I by definition of a block cipher. Of course, in practice, we want that both E and E inverse are efficiently computable. Again, that means if you know the inputs, you can easily get the output. Already this leads to several security requirements. We want the adversary looking at ciphertext to have a hard time figuring out what the plaintext were. So going from the Y's to the X's should be hard. Even more basic is that it's hard to get the key, and this is the first piece of security intuition that we need to grab onto, which is that when you see results of the block cipher created under a hidden key, it should somehow, for some reason, be difficult to actually lay your hands on the key. And otherwise, the adversary is as empowered as Bob. If it could actually obtain the key from these outputs, well, then it could use the inverse cipher, apply them to the key and the outputs, and get back the inputs, and we would have no security. So the key, as the word indicates, is the key. So with that, let's just look at an example, and we'll start with the most basic one, which is the data encryption standard. So the data encryption standard isn't in use anymore, but it's a classic design, both of historical importance and of technical importance, and its story still embodies many lessons and ideas that are worth looking at. And so it's worth seeing how it evolved and what happened to it. And it's a very interesting story. So for much of the existence of cryptography, it was viewed as a military subject. It was mainly, cryptography was developed for military applications. But by the early 70s, there was felt a need for a commercial and non-military use of cryptography. And this led the National Bureau of Standards, now called the National Institute of Standards and Technology, to look for a block cipher to standardize. That means that they wanted to publicly post the algorithm so that everybody could use it and have some sort of government backing that, yes, it has been validated in some way for security. And there were not many designs out there at the time, not many people doing this, but IBM was running an effort at the time to design a block cipher they were calling Lucifer. And working with IBM, the NSA turned it into what eventually became the data encryption standard. It was very successful. It was adopted as a standard by the American National Standards Institute, American Bankers Association. It's used in ATM machines and was used for many, many things. And early in the 2000s, it was eventually replaced by AES, but it still had a 25 to 30 year run. So what does it mean that it's a standard? It means that there's a public document, in this case put out by the Federal Institutes of Processing Standards, which has a certain number, and that document says in full detail how the algorithm works. It's not the job of this document to say anything about why they think it's secure, but clearly they picked it because they think it is, and a lot of work did go into that. But the document should allow anybody, anywhere, to implement that algorithm and to create, and for different people to create interoperable and compatible implementations. As you can see here, the standard, after being published, was reaffirmed. This was even up to the late 90s. When they first introduced it, they thought it would have a short lifetime, but it kept getting reaffirmed. And this one, remember, started in the 70s, was in 99. Okay, so before we get into it, maybe we can look at a few things about it out there. This is the Wikipedia page for DES, a nice reference where you can see a rough idea of history and length. It goes into more history than we've done. It'll cover many of the things we will also discuss. It talks about how it started from IBM, about the NSA's involvement, about concerns with the NSA's involvement due to whether or not they planted backdoors or not. You can see controversies. For example, a member of the DES team says, "We developed it entirely within IBM. The NSA didn't dictate a single wire." But in contrast, a declassified NSA book says that NSA began working on its own algorithm because the first offerings were disappointing, and then they kind of worked on these things together. There were disagreements about key length. So they started with the idea of IBM started with the idea of a 64-bit key, and the NSA convinced them wanted to reduce it to 48, and ultimately they compromised on 56. Interesting to speculate on why, and when we see how key length impacts security, we'll have reasons for that type of speculation. There were continuing concerns about things being hidden in them. There's a chronology, a description of the standard. You can see the 70s. It was first approved as a standard in 76, published in 77. Various attacks come in, and then the reaffirmation start in the 80s and so forth. Attacks were discovered in the early 90s. Nonetheless, it's reaffirmed here because the attacks were not found to be of real practical damage, and even here. And here finally AES comes in. And you can see that Wikipedia shows you a bit of a description. Here you can see the full FIPS standard. So this is it's an archived publication because the standard is no longer active, and it tells you it's the 46.3, was withdrawn in 2005. So it's no longer a standard, but you see that all the details of how it works are present in here. It's interesting to read how they write and specify these things. They show you the structure here that we're going to study, and different components and things like that. Okay, so what does DES look like? It has a key length and a block length, being a block cipher, of course. So that means that it maps 56-bit keys and 64-bit inputs to 64-bit outputs. and so does the inverse. These key and block length parameters are quite important for security, and so their values will enter many discussions and estimates. The high-level structure of DES is quite simple and works like this. Remember, the algorithm will take a 56-bit key as input and also a 64-bit message. So 2 inputs, but we write it this way just because usually the key K is fixed and M will vary. It first runs an algorithm called a key schedule, which takes the 56-bit key and produces 16 48-bit subkeys. Each of these has 48 bits, and there's 16 of them. Why? Because there are 16 rounds in the design. How does the key schedule work? It's a fixed function. Again, if you like, you can look in the standard. It'll tell you exactly how the key schedule works in some part of the standard. But we won't show that here. The message is then processed with something called an initial permutation, and that shuffles bit positions and gives you another message continuing to be 64 bits. We can ask why that happens and how it happens, and we'll think about both in a little bit. But first we want to get to kind of the main operation, and that consists of 16 rounds represented by a for loop, and each round works as follows. In any round, you start with a 64-bit string, which you break into two 32-bit halves. So at first it's the message itself, which is we break up as left half and right half, each 32 bits. And as you go on, you produce more of these halves. What each round does is the following. It needs to take these two 32-bit left and right halves and produce new output 32-bit left and right halves. The left half of the output is easy. It's just a copy of the right half of the input. Very simple. The right half of the output is more involved. You take the right half of the input, you run a certain function f. This function depends on the key. This is important because this is the first place the key was involved. If you don't involve the key, there's no security to be had. Anybody can invert this. And the key involved here is actually the subkey corresponding to this round. And we'll have to say how this function works, but it returns 32 bits. That is XOR to these 32 bits, and you get your right half. Now, of course, there are questions. What is this function f? Why this structure? One of the merits of this structure is that it gives you the block cipher property, or the property that once you fix and know the key, you have a permutation on 64 bits. You can see that by seeing that if I give you these outputs and you know the key, you can recover these inputs uniquely. How do you do that? To recover this is easy. You just copy this over. This diagram shows it in that way. So you go from here and you recover this over here. Now, how do you recover this? Well, once you have this, you run it forward through f. F is not invertible. You don't have a way to go backwards on f. But you run r forward through f. You know the key, so you can do that, and you get this value over here. If you add this into that, you will recover this because of the symmetry of the XOR operation. So this shows us that the permutation property will hold at least for these rounds. We've shown it for one round, but of course permutations compose, so it will carry over to 16 rounds. When you have your 16th round completed, you run it through the inverse of this permutation. This is a permutation on 64 bits, unkeyed, and that result is the ciphertext. Now immediately all kinds of questions can come up. For example, why these permutations? They have no effect on security since they're unkeyed. Anybody can perform this permutation and can here unperform it and recover this. So it can't possibly add to security. And the best we know is that it has something to do with how implementation proceeds with wiring and things like that. So with that as the high-level structure, we can start looking more at internals. Before we do that, let's, however, write down the code for the inverse function. That simply takes our picture and turns it into formulas, just to be sure that we know that we can write in the inverse function. Okay, let's start with a few details. We'll omit the key schedule by thinking about the initial permutation. What is it? It's a fixed table that you can see in the standard. Remember, that means that it's entirely public. Everybody knows this table. They need to know it to implement the algorithm. The way you read the table is that you have a 64-bit input and a 64-bit output. The first bit of the output is the 58th bit of the input. The second bit of the output is the 50th bit of the input. Third bit of the output is the 42nd bit of the input, and so on. This being a permutation, which you can check by seeing that there are no repeats in this whole sequence of 64 numbers, means it has an inverse, and that defines the function that happens here. Now again, one can ask, okay, they're mapping things like this. Why exactly? Why these particular positions? It's not so clear. Do they look random? Not clearly. For example, here you see even numbers, odd numbers in sequence. Similarly here and here. Similarly here and here. So column-wise, it's actually very structured, right? You see the even numbers here, the odd numbers here. It's a mystery why that's the case. In any case, as we saw, that has no particular impact on security because it's unkeyed. The heart of the design is this f function, right? So let's take a closer look at the f function. Remember, it takes a 48-bit key. This is the sub-key corresponding to the round. It's called once in each round, 16 times total, each time with the corresponding sub-key. And it takes a 32-bit input, not 64, but only 32, the right half. And it needs to return another 32-bit right half. How does it do that? It first applies a function called the expansion that takes 32 bits and outputs 48 bits. What is that function? Again, it's some kind of table. This tells you that the first bit of the output is the 32nd bit of the input. Second bit of the output is the first bit of the input, and so forth. Given that this extends 32 bits to 48, you will of course see repeats. So for example, the first bit is used twice. It's the second bit of the output and the 48th bit of the output. You again see that this is not random looking. There's quite a bit of structure. 1, 2, 3, 4, 5. And then you start from here and go this way. Then you stagger a bit. Here you see the structure being repeated. You take the second last thing, go sequentially from there, and so forth. Okay, why do we want 48 bits out? Because that's the length of the sub-key, and now you can do an XOR. Now this again is a crucial step because this is the place key material gets involved with the input. Remember, R comes from the input. It's now getting added into key material, and this coupling is where the mixing happens. You now have a 48-bit string. We break it into blocks. We view it as 8 blocks, each block being 6 bits long. 6 times 8 is 48. Okay. We now take each block, which is 6-bit, and compress it down to 4. That is done for each block by a function called S, and this is called an S box. There's an S box for each value of I. We now have 8 blocks, each 4 bits long. 8 times 4 is 32. We have the right length for the output. For good measure, we permute that, however, before outputting, again with some fixed permutation described in the usual way. And that's the output. This is the output of the f function. Remember, it goes through all that Feistel round stuff. If I didn't say it earlier, the structures are called Feistel, the rounds that we saw earlier. So again, we have a pretty clear structure at this level, but we still don't know what goes on inside these S boxes. and we have to see how they're designed. And their design team turns out to be the heart of it. They're crucial for security. And how do they work? Well, they're actually just tables. So again, these are public tables. You can see them in the standard. And everybody who implements the algorithm needs to know exactly how they work. But there are no secrets in the tables themselves. The way you read it, remember that each S box is compressing a 6-bit input to a 4-bit output. We view the 6-bit input as 2 bits and a number between 0 and 16 and 15. So 4-bit number and additional 2 bits. And then you look up the corresponding output, which is also a 4-bit number in the table. And there are 8 of these boxes. I only showed 3 of them. Now, if you look at these boxes, they look quite mysterious. And what we know is that a significant effort has gone into their design. These are not ad hoc chosen or very quickly chosen boxes. They're carefully structured and designed to achieve security against various types of attacks. And as time passed, we realized how well or how poorly designed they were. Mostly, in fact, how well designed they were. So that's kind of how DES works. And we can again go back to the standard, and now we see that it shows you, for example, initial permutation and its inverse are here. It shows you the F function over here, pictorially, which we described, the expansion table over here, and then the ending permutation, and so forth. And where will we find, for example, the key schedule and so forth? Well, there are appendices and other things which will describe things like that. So again, this contains everything you need to implement the algorithm.